Good evening, students. So today we are going to discuss problems from rotational motion. So this is the first question. Three particles A, B and C, each of mass m, are connected to each other by three massless rigid rods to form a rigid equilateral triangular body of side L. And is hinged. This body is placed on a horizontal frictionless table XY plane and is hinged at point A so that it can move without friction about the vertical axis through A. The body is set into rotational motion on the table about this axis with a constant angular velocity omega. First bit, find the magnitude of horizontal force exerted by the hinge on the body. Now when bodies rotate about fixed axis, then each and every point on the body will be moving in a circle about with center on the axis of rotation, and all the points of the body will have same angular velocity, same angular acceleration, same angular displacement. Angular variables are common to all the points of the body. It is called pure rotatory motion. Then if it is rotating with constant omega, then all the points will have only radial acceleration, which is given by omega square r, which is directed towards the center of that circle around which it is moving, that point. Okay. And if omega is varying, then they also have tangential acceleration. Tangential acceleration is given by r alpha. And how do you find alpha? Is torque by moment of inertia. Torque about the given axis and divided with moment of inertia, you will get alpha. Then what is acceleration of any point? It is resultant of radial acceleration, that is omega square r, and tangential acceleration, that is r alpha. That is what you have to see. But in this question, they have given the body is set into rotational motion on the table about this axis with a constant angular velocity omega. Then what is the horizontal force exerted by hinge on the body? Then what is net external force on the system? When a body is rotating, different points will have different accelerations, and center of mass of the system also moves in a circle. Then what is net external force on the system? Net external force on the system is equal to total mass into acceleration of center of mass. Acceleration of the center of mass also radial and tangentially you have to find. So in this case, all the three particles rods are massless. This is earlier IIT question only. So where is center of mass? Will be at centroid. So center of mass is somewhere here at O, and this distance is L by root 3. That distance is L by root 3. Okay. And if it is rotating with constant omega, then what is the acceleration of center of mass will be in this direction towards center. What is the acceleration of center of mass is AR, let us say. Then what is AR? Is omega square into L by root 3. Then what is net force acting towards axis of rotation? Is total mass into acceleration of center of mass. Total mass into acceleration of center of mass. What is total mass? 3m into acceleration of center of mass. That is net force, and that force is in horizontal plane. The triangular frame is rotating about this axis in horizontal plane, and z axis is vertical, where gravitational force is vertically downwards. So the hinge reaction, the force by hinge at hinge, there will be a vertically upward force which should balance mg, but that is not in horizontal plane. So in the first bit they are asking only the force in horizontal plane. Horizontal force exerted means the forces in horizontal plane. So only force is towards center, that is given by 3m into AR, where AR is omega square into L by root 3. Okay. Next bit, at time capital T, when slide BC is parallel to x axis, force F is applied on B along BC. So there is a force applied on B along BC. Obtain the x component and y component of the force exerted by hinge on the body immediately after time t. Now immediately after this force is applied, what is x component of force and y component of force? That is what they are asking. Now it is still rotating with omega, then we have applied some force. So this force will produce torque. So because of that, it will acquire angular acceleration. angular acceleration. How do you find angular acceleration? It is force into perpendicular distance. So, force is applied in this direction. So, force into this perpendicular distance, that is L root 3 by 2, that is torque. So, force into L root 3 by 2 equal to I alpha. I alpha. What is I? Moment of inertia about this axis. For this particle ml square, for this particle also ml square. What is moment of inertia? 2 ml square. 2 ml square. That is moment of inertia. So, if I substitute this moment of inertia value here, we can find alpha. Okay. Once you know alpha, now there is a tangential acceleration for center of mass also. Radial acceleration we have already calculated. That is radial acceleration. At that instant, because there is a torque, angular velocity will change. There will be tangential acceleration. What is tangential acceleration? Is in this direction. It is about to move like this in a circle. So, tangential acceleration is along the tangent in this direction. And what is tangential acceleration? It is L root 3 by 2 into alpha. That is tangent, not L root 3 by 2. L by root 3 into alpha. What is tangential acceleration? R alpha. What is R? L by root 3. So, L by root 3 into alpha. This is tangential acceleration. Now, how do you find x component of y component of hinge force? Is this only, whatever you have found out earlier, okay, 3m into AR. What is x component of hinge force? Let us say x component of hinge force is Fx. Then what is net force acting on the system triangular frame along x axis? Is this F plus Fx equal to total mass into acceleration of center of mass along x axis, which is nothing but at. Okay. So, what is the equation you should write? F plus Fx equal to total mass into at. Then Fx you can find. Okay. Y component is this force, x component is this force. And if they ask net hinge force, there is z component also. Z component of hinge force in upward direction, that should balance mg. So, net force by hinge on the triangular frame means it is Fxi bar plus Fij bar plus along z axis, that is mgk bar, okay, 3 mg. I think you have followed. Any doubt? Okay, we go to next question. Now, this is next question. Thread is wound on a solid sphere of mass small m and radius small r placed on a plank of mass capital M. The other end of the thread is attached to the plank. After passing over two light pulleys as shown, a force capital F is applied on the plank and the system starts moving. There is no slipping at any contact point of the sphere. The contact between plank and plane is frictionless. So, there is no friction here, but there is friction here. Find the acceleration of center of mass of the sphere. Now, how do you find acceleration of center of mass of the sphere? One method is you can do by force, because there is no slipping here. What type of friction acts is static friction. Okay. So, if I assume acceleration of center of mass of the sphere is A and angular acceleration is alpha, angular acceleration is alpha, okay, anti-clockwise. Acceleration of center of mass is towards left, and acceleration of this plank, let us say, is A1 towards right. So, first equation is, if I write no slipping condition here, what is the acceleration of the point on this disc or sphere, whatever it is, that should be equal to acceleration of the plank. So, what is the acceleration of this point? Because of rotation, r alpha towards right, and because of translation, a towards left. So, r alpha minus a equal to a1, that is first equation, that is equal to a1. Okay. Next, because actually there is a string here which is not displayed here. Okay. Now because this point and this point are connected by a string directly, acceleration of this point, this end of the string towards right, should be equal to acceleration of this end of the string towards left. Okay. So what is the acceleration of this end of the string? Is a plus r alpha towards left. A because of translatory motion and r alpha because of rotatory motion. So a plus r alpha. That should be equal to acceleration of this end is a1. Okay. So from these two equations you can find relation between everything in terms of other you can write. Okay, if I add these two, you'll get 2a1 equal to 2r alpha. So a1 equal to r alpha. Okay. Add these two, a cancels, you'll get 2r alpha equal to 2a1. So a1 equal to r alpha. If I put a1 equal to r alpha here, a is 0. A is 0. Okay. A is 0. So means it is only rotating, not translating. But this is translating. Okay. And what type of friction is acting here? Static friction. Now if I write force equations and torque equation on this force equation, and torque equation, okay. So on this solid sphere, what are the forces acting? Tension in this direction. And frictional force is small f towards left, let us, towards right. It is static friction. How much it acts is small f, let us, towards right. Then what is force equation? Acceleration of center of mass is 0 we have got. So net force has to be 0 in the horizontal direction. So T minus F is equal to 0 or T equal to F. Then torque equation if I write T into R plus F into R means 2T into R, because T equal to F equal to I alpha. What is I? 2 by 5 mr square into alpha. Okay. But what is R alpha? Is A1. So I can replace R alpha with A1. Then one R cancels. Okay. And R alpha with A1 and 2 also cancel. So what do you get? T equal to MA1 by 5. MA1 by 5. Okay. So first bit answer is 0 anyhow, acceleration of center of mass of the sphere. Now if I write down forces on the plank, what are forces on the plank? One force is applied force towards right and frictional force towards left and tension towards left. Then what is the force equation? F minus T. But what is the small f? Is capital T. So F minus 2T equal to capital M into A1. Capital M into A1. Okay. So in place of T, you can put small m A1 by 5 here. You will get A1 if I solve. Okay. A1 in terms of capital F. And tension also you can find once you know A1, substitute A1 value here, you will get tension. Okay. And frictional force between sphere and plank is nothing but tension in magnitude. Okay. Such questions you can do by energy method also. Means for example, if I give one more question like this, let us say this is a hollow sphere I will take, radius r, mass m, hollow sphere, and here friction is there sufficient to make it roll, and this is a string and this is a pulley. Pulley is smooth and massless, and some other block is hanging here. Mass is capital M, this is small m. There is no slippage here, okay, between ground. This is hollow sphere. Then find acceleration of the block. Then find acceleration of the block. Now such questions are there. You can write force equations and torque equations and rolling conditions and do. That is one method. Other method is we can always do by energy method, okay. So first of all, if I use force equation and torque equation, for example, let us say acceleration of center of mass is A and angular acceleration is alpha. Angular acceleration is alpha. Then let us say frictional force is acting towards left on this, okay. Then what is force equation? Tension is towards right. So T minus F is equal to ma. Then what is rolling condition? Acceleration of the lowest point with respect to surface should be 0. Means A minus R alpha is 0. So A equal to R alpha. A equal to R alpha. Then torque equation. What is torque about center of mass? T into R, clockwise moment. F into R, this is also clockwise moment. So both clockwise moments gets added. So you'll get T plus F into R equal to I alpha. What is I? 2 by 3 mr square, hollow sphere about center of mass, okay, into alpha. So when R cancels, R alpha is A, you'll get, so 2ma by 3 you'll get, okay, 2m A by 3. And if I add these two equations, you'll get 2t. 2t equal to 5m A by 3, okay, 5m A by 3. Then A value you can find 60 by 5m. And here, what is its acceleration? Let us say A1. It is only translating. Then how do you find relation between A1 and A? Acceleration of this point on the string should be equal to acceleration of this point on the string. Acceleration of this point towards right should be equal to acceleration of this point downwards. And acceleration of this string equal to acceleration of the sphere with which it is in contact at that point, because there is no slippage at that point. So what is the acceleration of the highest point? Is A plus R alpha, that is 2A in this case. So that is acceleration of the point on the string towards right. So for this block also it should be 2A. Okay. So what is the equation for this block? Capital Mg minus T equal to capital M into 2A. Capital M into 2A. And 2T equal to 5ma by 3. Means T equal to 5ma by 6. That value is substituted there. This is small m, that is capital M, we will get, okay. This is by force and torques method, okay. If you do by energy method, we'll assume, let us say, it moves by y, let us say it moves by x, then it comes down by 2x. If acceleration of this center of mass of this sphere is a, then its acceleration is 2a. If velocity of center of mass is v and angular velocity of this sphere is omega, then velocity of this block is 2v. So if center of mass of this sphere moves by x, this block should come down by 2x. And after moving by x, if its center of mass has acquired a velocity v, this block should acquire a velocity 2v. Okay. Now we consider these two as system. These two as a system. Then it has moved by x. Then it has come down by 2x. At that instant, let us say its velocity is v and angular velocity is omega. But because it is rolling, v equal to r omega. And at that instant, what is its velocity? 2v. Now if I apply energy conservation for the system, what is the only force doing work on the system is gravitational force on capital. Friction here, it won't do any work. Static friction, it is not doing any work, okay. And this tension do not work on the, won't do any work on the system. So only force doing work is gravitational force on this block. So what is work done by gravitational force on this block is mg into 2x. That is equal to gain in kinetic energy of the system. So what is kinetic energy gain for this block? Half into capital M into 2v whole square. Plus, for this what is kinetic energy? It has translational kinetic energy and also rotational kinetic energy. So it is half small m v square plus half I omega square. But when any body is rolling on a fixed surface, then what is kinetic energy? When a body is rolling on a fixed surface, then kinetic energy is given by half mv square into 1 plus gamma, that is kinetic energy, where its moment of inertia about center of mass is gamma mr square. If I write like that, if I write its moment of inertia about center of mass as gamma mr square, then its kinetic energy is given by half mv square into 1 plus gamma. In this case, gamma is 2 by 3 because it is hollow sphere, okay, where m is mass and v is velocity of center of mass. Here, half mv square is translational kinetic energy part and gamma half mv square is rotational kinetic energy part. What is the ratio of translational kinetic energy to rotational kinetic energy? 1 is to gamma. 1 is to gamma. So in this case, what do you get? Half small mv square into 1 plus gamma, that is 1 plus 2 by 3, that is 5 by 3. Okay. So from here, you will get v square in terms of x. V square equal to some constant into x. Okay. This constant is nothing but 2a. If I compare this with v square minus u square is 2ax, I have assumed when it has moved by x center of mass, its velocity is v and center of mass is moving with uniform acceleration. So for center of mass, I can use v square equal to v square minus u square is 2as, u is 0. So v square equal to some cx if I write. What is the acceleration of center of mass? If I compare this with that v square minus u square is 2x, it is coefficient of 2a, coefficient of x is 2a, okay. If I make coefficient of v square 1, that you can compare, or you can write v dv by dx, that's up to you. You know v in terms of x, then how do you find acceleration? V dv by dx. But anyhow it is constant acceleration, you can compare that with v square minus u square is 2as, okay. One more question I will give you, try once and tell, okay, similar question. Now this is a pulley, inner radius is r, outer radius is 3r and pulley is fixed, free to rotate about C. It is free to rotate about a horizontal axis passing through C in a vertical plane. Moment of inertia of the pulley is 4mr square and one block is connected here, its mass is 3m and other block is connected here and its mass is 4m, okay. This pulley is fixed, free to rotate but cannot come down or neither go up, it cannot translate, it can only rotate about an axis passing through C, okay. Find acceleration of 3m and angular acceleration of pulley. Find acceleration of 3m and angular acceleration of pulley. Take 5 minutes and try all of you, then we will see. If you have completed, you can tell the answer, okay. Okay, anyone did you complete? Here also we can do by force method, but energy is better. Okay. Now will 3m come down or 4m comes down? Now if I keep 4m here, what block we have to keep it here so that the system is in equilibrium? If I consider torque about this point, let us say here capital M is there instead of 3m and here 4m is there. Then when this system is in equilibrium, when torque due to this capital M force, that gravitational force which produces clockwise moment and this is anti-clockwise moment, both of them balances, then the system is in equilibrium. Means capital Mg into R is equal to 4mg into 3r. Then the system is in equilibrium, means capital M equal to 12r. Capital M equal to 12r. So if I keep here 12 small m, if I keep here 12 into small m, then they are in equilibrium. Okay. If I keep here less than 12m, it should go up, then it will come down. And if I keep here more than 12m, this will come down, this will go up. But even then, if you don't know that also, you can assume one of them goes down, other goes up, it doesn't matter. Okay. We will get negative finally in the answer. So for example, let us say I'll assume it goes down. Okay. It goes down and it goes up. Then what is the relation between velocities? So let us say it goes up by x. In some time t, it goes up by x, let us. Then how much it comes down? Angular velocity of this is omega, which is changing continuously. At a particular instant, its angular velocity is omega. Then what is velocity of this point? R omega upwards. That is equal to velocity of this point. Okay. So what is velocity of this point? R omega. At an instant when its angular velocity is omega. And what is velocity of this point? 3r omega downwards. Means its velocity is 3 times this. Means if it goes up by x, it should come down by 3x in any given time. So assume it goes up by x, it has acquired a velocity v. And in the same time, it should come down by 3x and it has acquired a velocity of 3v. And at the same instant, its angular velocity is omega, let us. Now write energy conservation. So what is the only force doing work on the system is gravitational force on the two blocks. So what is work done by gravitational potential energy? I am fine. Now work done by gravity you should do. Okay. What is work done by gravity or loss in gravitational potential energy? What is loss in gravitational potential energy of the system? For this 3x. Okay. It goes up by x, it comes down by 3x. Then 4mg into 3x, that is 12mgx. At the same time it has gone up by x. So how much it has gained? 3mgx. So what is net loss in gravitational potential energy of the system? Is 12mgx minus mgx, that is 9mgx, equal to gain in kinetic energy. What is gain in kinetic energy? Translational kinetic energy of these two and rotational kinetic energy of this block, this pulley. Okay. So what is translational kinetic energy of these two? Half 3mv square plus half 4m 3v whole square plus half I omega square. Half I omega square. Okay. What is I? 4m r square into omega square. But what is r square omega square? Is v square. Okay. That's all. Once again, if I simplify this, m cancels anyhow. What do you get here? 3v square by 2 plus 36. 3 plus 36 is 39. 39 plus 4, 43. Okay. So 43 v square by 2. So what is v square? 18gx by 43. If I compare this with v square equal to 2ax, what is the acceleration? This is 2a. Okay. So what is the acceleration? Is this by 2. So that is 9g by 40. So that is the acceleration of this block. Because I have assumed it moves by x, it acquires a velocity v. At the same instant, what will be its acceleration? Triple, 3 times. Followed? Followed? We can find angular acceleration of this also. What is angular acceleration of this? If its acceleration is a upwards and its angular acceleration is alpha, what is acceleration of this point? R alpha upwards equal to a. So a equal to r alpha. So what is alpha? A by r. Alpha is a by r. Okay. So one more question I will give. Similar question where you can do by energy, that is better always. Now this is solid cylinder will take. Mass is m, radius is r, okay. And on this we have kept a Planck. Planck mass I will take 2m. And we applied a force F on this. Then find acceleration of the Planck. Find acceleration of the Planck. Find acceleration of the Planck. That is first bit. Second bit. Find work done by frictional force between Planck and cylinder on Planck. Find work done by frictional force between Planck and cylinder on Planck in a time t. In a time t. So in this case also, if they ask frictional force and all those things, first of all we can find acceleration, then we can write, okay. But how to find acceleration? On this cylinder, there are two frictional forces acting. One is here by ground, other is between Planck and cylinder. On the Planck, there are two forces acting. One is applied force, other is frictional force here. Okay. Then we can write force equations and torque equations and do. Other method is energy method. So once again, if I assume at any instant if its velocity is v and angular velocity is omega, what is the relation between v and omega? Because it is rolling on a fixed horizontal surface, v should be r omega. And what is velocity at the topmost point? Is v plus r omega, that is 2v. So when velocity of center of mass of this cylinder is v, then velocity of topmost point should be 2v, which is nothing but velocity of the Planck. Okay. Velocity of the Planck. Now let us say in any given time, therefore the center of mass of the cylinder moves by x, then this Planck should move by 2x, because its velocity is double the velocity of center of mass. Okay. And now after moving, center of mass moves by x, the center will acquire a velocity v, let us say. Then Planck should acquire a velocity of 2v. Then once again take system and apply work energy theorem. What is the only force doing work on the system? Is this applied force. The friction here won't do work, and friction here will do work on Planck, it will do work on cylinder, but total work done will be 0 because it is static friction. Okay. So what is work done by this applied force? When this has moved by x, this Planck moves by 2x. So what is work done by applied force? F into 2x. That is equal to, what is kinetic energy gain for the Planck in that time? Half into 2m into 4v square, plus kinetic energy gain for the cylinder, half mv square into 1 plus gamma, because it is rolling on fixed horizontal surface. Half mv square into 1 plus gamma. For a solid cylinder, what is gamma? Half. So 1 plus half, that is 3 by 12. So what do you get? 8 plus 3. So into 2 by 2, if I do 16, I will get 16 plus 3, 19. 19 mv square by 4. So what is v square? 8fx by 19m. So once again, if I compare this with v square equal to 2as, what is acceleration? 4f by 19m. Okay. Okay, that is acceleration. So what is acceleration of center of mass of the cylinder? 4f by 19m. Then what should be acceleration of the Planck? Is double that, 8f by 19m. Okay. Now what is next to be tasked? What is work done by frictional force between these two on the plank in that time? Okay. Now if I can, then we can apply work unity theorem for the plank. Okay. In that time, in a time t. So in a time t, what is velocity acquired by plank after time t? V equal to u plus at can use. What is velocity acquired by the plank after time t? V equal to at, that is 8f into t by 19m. Okay. In that time, how much plank moves? Half at square. Half at square. Okay. Then what are the forces doing work? Let us say plank displaces by s in that time. S. What are the forces doing work on the plank? One is applied force, other is frictional force. So what is work done by applied force is F into S plus work done by friction equal to change in kinetic energy of the plank, that is half into 2m into V square. That's is this V, not that V. Okay, that is velocity of center of mass you are taking. Okay. What is S? You know, S is half at square. S is displacement of plank, that is half at square. Okay. Actually, the friction here, it won't do work on the system, and friction here is not at all doing work because it is rolling on fixed horizontal surface. So directly what is work done by friction here is equal to change in kinetic energy of the cylinder. You can write only force doing work on cylinder is this friction, and how much work it will do on the plank is negative of that. So instead of finding on plank, even though they have asked on plank, you find work done on the cylinder by this friction and take negative of that, we will get work done on the plank. For example, in the same time t, what is the velocity the plank acquires, cylinder acquires, is 4f by 9m into t. This is velocity it acquires. And what is the only force doing work? What is the only force doing work? Is friction between these two on the cylinder. So work done by that friction equal to gain in kinetic energy, that is half m v naught square into 1 plus gamma, that is half. That's okay. I am South Indian, but I know Hindi, but now Hindi classes are separately going on. Okay, you can attend those classes on the same topics. Classes in Hindi, they are separately holding. Okay. This is the method where you can do by work unity theorem. Otherwise, you can always do by force method and torques and all those things and acceleration conditions, rolling conditions like that. Okay. So next question we will see anyhow. This we are done already. Now this is next question. The arrangement shown in figure consists of two identical uniform solid cylinders, each of mass small m, on which two light threads are wound symmetrically. Find tension of each thread in the process of motion. The friction in the axle of the upper cylinder is assumed to be absent, and they are moving in such a way, string is unwinding everywhere. That's what they should give actually. Okay, string is unwinding everywhere. Okay, and both cylinders they have given same mass. This is a problem from Irido. Okay, now I will draw side view. Okay, I need not draw entire figure, I will draw side view. If I draw side view in next page, we will get like this. But this is fixed. This is fixed cylinder, radius r mass m. This is also radius r mass m, but this is free to translate, and it can also rotate about center of mass. Let us say its center is C1, it is C2. Okay. Now this is fixed, it can only rotate. Now you have to find tension and acceleration, angular acceleration, everything. So assume acceleration of center of mass of the cylinder is A or A1 and angular acceleration is alpha 1. And for this only angular acceleration, that is alpha 2, let us alpha 2. Now what is force equation for this? Tension in the string is T, let us say. First of all, I will write this. Tension is downwards. So what is equation? Torque equation. T into R equal to I alpha. What is I? mr square by 2 into alpha 2, that is. Okay. Then R cancels, you will get T equal to m into R alpha 2 by 2. That is one equation. Next, this cylinder, if I come, what are the forces acting? One is mg downwards and tension upwards. Here I did not consider mg because it is not translating. Mg will act at center of mass, it is fixed. So mg I need not consider because it cannot produce any torque because it is free to rotate about center of mass. Okay. Here we have to consider because it is translating and also rotating. Okay. Now here force equation, if I write, what do you get? mg minus t equal to ma1. Then torque equation about center of mass, that is T into R equal to mr square by 2 into alpha 1. Then R cancels, you will get T equal to mr alpha 1 by 2. But how do you find relation between alpha 1, A1 and A2? We should consider once again acceleration of this end of the string is equal to acceleration of this end of the string. Acceleration of this end of the string in downward direction should be equal to acceleration of this end of the string in downward direction. What is acceleration of this end of the string is R alpha 2. That is equal to acceleration of this end of the string in downward direction is A1 minus R alpha 1. Okay. That's all. Then you can find T value first of all. What is alpha 2 in terms of T, you know? Alpha 1 in terms of T, you know? Actually alpha 1 equal to alpha 2 you will get from here directly because LHS is same for both of them. Okay. So what do you get here? If I bring it to LHS, 2R alpha 1 I will get. 2R into alpha 1. What is R alpha 1? 2T by M equal to A1. What is A1 in terms of T is G minus T by M. That's all. Okay. If I bring this T by M to LHS, what do you get? Phi T by M equal to G. So what is T? Mg by 5 will get. So tension in the string is mg by 5. Then you can find A1, A2 and alpha 1. Okay. Followed? Any doubt? Okay. Next question we'll see. Now this is next question. A small body A is fixed to the inside of a thin rigid hoop of radius capital R and mass equal to that of the body capital A. The hoop rolls without slipping over a horizontal plane. At the moment when the body A gets into the lower position, the center of the hoop moves with velocity V0. At what value of V0 will the hoop move without bouncing? Hoop move without bouncing. Okay. Will you try by taking 3 minutes? This is a problem for irido only actually. This is a small particle which is fixed to hoop. Hoop means circular ring. Hoop means circular ring. Take 2 minutes or 3 minutes, you try once, all of you. I will add 1 or 2 questions to this, okay. Same problem. You take 2 or 3 minutes and try, all of you. Now, these are rolling problems. Okay. Anyone, did you complete? Okay. So, these are rolling problems. Now, this is a hoop. Hoop means circular ring, and there is a particle fixed to the bottom of the ring initially. At that instant, velocity of center of mass of the hoop is V naught. Center of mass of the hoop. Okay. Hoop and that particle have same mass. Okay. Now, so what type of friction is acting? Because it is rolling, that's what it is mentioned in the problem. Static friction acts. Once again, that static friction is not doing any work because it is rolling on fixed surface. Even if it is moving on a moving surface also, net work done by static friction on the system will be 0. Individually it can do work on each body, but on the system static friction never do work. Kinetic friction always does negative work on the system. Okay. Now, if I consider this is the particle here, where is center of mass of the system of hoop and the particle is here at a distance r by 2, and as it is rolling, the center O only translates, it moves in a straight line, and all the points will rotate about center with respect to center. With respect to an outside person, they are moving some path which is called cycloid. Okay. But with respect to center, all the points will move in a circle. So, center of mass of the system as it is translating will be moving in a circle about O. It will be moving in a circle about O with radius r by 2. Okay. So, once it completes one full circle and comes somewhere here, center of mass of the system also moves in a circle like this and comes here of radius r by 2. Okay. Now, the center of the hoop moves with velocity V naught. At what value of V naught will the hoop move without bouncing? Now, as it is moving like this, center of mass, because center of mass is moving in a circle, net force on the system is not 0, because center of mass will have an acceleration, and that way it is moving in a circle with its speed changing. Therefore, there is tangential acceleration and also radial acceleration. Okay. But center O is moving with some velocity which is changing. Okay. Now, as it is moving like this, at the lowest point, what are the forces acting? Normal force by ground will be upwards and total gravitational force 2 mg downwards. Okay. So, what is normal force? Initially, if they ask, they did not ask, okay, but if they ask, how do you find equation? How do you write equation? Net force on the system equal to mass into acceleration of center of mass. Okay. And friction also acts. At this point, center of mass will be moving in a circle like this. At this point, what is velocity of center of mass with respect to center of the hoop? With respect to center of the hoop, velocity of center of mass is V naught by 2 towards left. Any doubt? Center of mass velocity is V naught. Center velocity is V naught. Then what is velocity of any point because of rotation is r omega, where omega is V naught by capital R because it is slipping on ground. What is rolling condition? V naught equal to r omega. So, what is velocity of this point? Velocity of this point with respect to ground is V naught minus r omega by 2. V naught towards right because of translatory motion, r omega by 2 towards left because of rotatory motion, where omega is V naught by r. Okay. So, what is velocity of this point? Absolute velocity is V naught by 2 towards right, but its velocity with respect to O you should take, that is V naught by 2 towards left, because it is circular motion with respect to O. With respect to O. Okay. So, what are the forces acting? In the vertical direction is n upwards, 2 mg downwards. Okay. So, what is the equation? N minus 2 mg equal to m into total mass into acceleration of center of mass towards center, that is V square by r. So in this case, what is total mass? 2m into V means V naught by 2 whole square by R by 2. That's what it is. So n value you can find initially. Initially, let us say it is n1. N1 you can find. Okay. But what is the question asked is, at what value of V naught will the hoop move without bouncing? Means as it is moving like this, center of mass, as center of mass is going towards left like this and going to the topmost point, the normal force continuously decreases. So if normal force do not become 0 at highest point, it do not become 0 anywhere, then hoop do not lose contact with ground. Okay. So where normal force is minimum at highest point. So at highest point it can lose contact, and at highest point if it do not lose contact, where normal force is minimum, it do not lose contact anywhere. So what is minimum value of V naught? So that it moves without bouncing, means we will assume normal force is 0 at highest point. Okay. So when it goes to highest point, what happens? When center of mass goes to highest point, assume velocity of center is V at that instant. Okay. Then what is velocity of center of mass with respect to center? Will be V by 2 towards right. Then what are the forces acting at that instant? Is normal force upwards, let us say n, and 2 mg downwards. 2 mg downwards. So what is the force equation you will get? Force equation is net force towards center equal to mass into acceleration of center of mass. What is net force towards center? Is 2 mg minus n equal to 2m into total mass is 2m. Okay. 2m into V by 2 whole square by R by 2. If I do that, you will get V square by R. I think here also same. Okay. 4 goes to numerator and 4 in denominator, you will get 4 cancels, you will get V naught square by R, and here V square by R, where V is velocity of center. Okay. So this is one equation, and if it just moves without bouncing, means at topmost point we will assume normal force is 0. So put n equal to 0, you will get V value. Okay. So V square equal to 2 mgr. Okay. M also will be there. Then m cancels. What is V square? 2gr. So velocity at this point is 2gr. Okay. Now energy conservation next. So when center of mass is here vertically below O, what is velocity of center is V naught. When it comes here, its velocity is V. Then when it goes from here to here, potential energy is gained, then kinetic energy is lost. Okay. So initial kinetic energy equal to gain in potential energy plus final kinetic energy. That is work energy theorem or conservation of energy will write. Okay. So what is initial kinetic energy of the system? Now finally, initially this particle is here at lowest point. So what is kinetic energy of the system initially? If velocity of center is V naught, what is kinetic energy of the hoop? It is half mv naught square into 1 plus gamma. Half mv naught square into 1 plus gamma means 2. For a hoop, what is gamma? 1. Okay. And what is kinetic energy of this particle will be 0 because it is at lowest point whose velocity is 0 at that instant. That is equal to, in the final figure, when this particle comes to topmost point, when center of mass is here, what is kinetic energy? Where velocity of center is V. Okay. What is kinetic energy of the hoop? It is half m V square into 1 plus gamma, that is 2, plus kinetic energy of this particle. Now if velocity of center is V and it is rolling, what is velocity of topmost point will be 2V. So what is kinetic energy of this particle? Half into m into 2V whole square, that is 4V square. Okay. Plus gain in potential energy. What is gain in potential energy? Center of mass has gone up by R. This is R by 2 and this is also R by 2. Then center of mass has moved up by R. Means total mass 2m has gone up by R. So what is gravitational potential energy gain? 2 mgr. That's all. That's okay. But what is V square? From here, if I put normal force 0 at highest point, V square equal 2gr. So V square equal 2gr if I put here, I will get 2 mgr here and here 4 mgr. 6 mgr plus 2 mgr, 8 mgr will get. What is V naught? Root 8 gr will get. That's all. Root 8 gr. So if velocity at lowest point, when this particle is at lowest point, when velocity of center of mass is root 8 gr, then when it completes half circle, then normal force becomes 0. Then it is just loses contact with ground, but immediately it come in contact with ground. So motion is smooth. But if its velocity is greater than root 8 gr, when this particle is at lowest point, it will lose contact somewhere where normal force become 0. Okay. Immediately after losing contact, what happens? Let us say if I give more than root 8 gr, then immediately after losing contact, the body starts rotating about an axis passing through center of mass. This translatory and rotatory motion will convert to pure rotatory motion. Pure rotatory means about center of mass, it will translate also, but it starts rotating about center of mass. Okay. Then also it translates and rotates, not pure rotatory motion, but immediately it starts rotating about an axis passing through center of mass. Okay. Followed? Now one more bit I will ask. If V naught is root 8 gr, that is what you have done. V naught is root 8 gr and center of mass comes here. At that instant, find normal force and frictional force. Find normal force and frictional force. Okay. So later I will tell. But actually we will do some rolling problems also. But before that we will see next question. Oh, this already we have done I think earlier. Similar question I have given. Okay, but we will see. In the pulley system shown, if radii of the bigger and smaller pulley are 2 meters and 1 meter respectively, and the acceleration of block A is, which is block A I did not mention, okay. Block A is 5 meters per second square in the downward direction. Then the acceleration of block B will be, okay, I will assume it is block A, let us, and this is block B. So let us say its acceleration is 5 meters per second square downwards. Then what is the acceleration of block B? Once again same relations, if angular acceleration of this pulley is alpha, which is rigidly fixed, means it can only rotate but cannot translate. Then what is acceleration of this point is 2 alpha downwards. And what is acceleration of this point? Alpha upwards. So if its acceleration is A, its acceleration should be 2A. So if it is 5, it should be 2.5 upwards. Okay. Acceleration of B will be 2.5 upwards, then D will be the answer if this is 5. Okay. And if they give this is 5, then this will be 10. This will be 10. Okay. But we will see rolling problems. Okay. Now any body, if it is rolling on fixed surface, as they give some velocity or angular velocity. Okay. Let us say this is center of mass C, and it is a hollow cylinder. I will take hollow cylinder, and center of mass velocity is V naught, and angular velocity is 2 V naught by R. Coefficient of friction is mu. Now if V equal to R omega on a fixed surface and velocity of lowest point is 0, if V equal to R omega, it may not be rolling sometimes, because both V and R omega for lowest point may be in same direction. Then it gets added, then it will be slipping. Okay. But if V equal to R omega and in such a way velocity of lowest point is 0, then it is said to be rolling. And If V is not equal to R omega on a fixed surface, it is not rolling anyhow, then it is slipping. Okay. If velocity of lowest point is towards left, then it is slipping backward, then friction acts towards right, kinetic friction. And if velocity of lowest point is towards right, it is slipping forward, then friction acts towards left. Okay. So friction acts, what type of friction acts now when it is slipping? Kinetic friction. And what kinetic friction will do? Kinetic friction acts to provide rolling, and static friction acts to maintain rolling. Static friction tries to maintain rolling. Kinetic friction tries to attain rolling motion. Okay. So kinetic friction acts to attain rolling. Okay. So if velocity is greater than R omega, kinetic friction acts to decrease velocity and increase R omega. So finally it starts rolling. If R omega is greater than V, kinetic friction acts to decrease R omega and increase velocity, so that it again rolls. Okay. Now this is the question. Write down. After what time it starts rolling? After what time it starts rolling? Now Hindi mein padhaiye means now that Hindi classes are going on separately. That's what I have told you earlier also. Okay. You can attend those classes. If you feel comfortable English also, you can attend these classes also, and both also you can attend. Okay. Now this is the question. Write down. This is the problem. Questions I will dictate. First bit is find after what time it starts rolling. After what time it starts rolling. Second bit, velocity of center of mass when it starts rolling. Velocity of center of mass when it starts rolling. And work done by frictional force until it starts rolling. Work done by frictional force until it starts rolling. So in such questions, when a body is rolling, then what is angular momentum about lowest point? Let us say when a body is rolling on fixed surface, fixed horizontal surface, or any surface also. Angular velocity is V, velocity is V, angular velocity is omega, and V should be R omega. Then what is its angular momentum about any point on this line? So for example, if I consider some point O here, schedule nahi pata chalta, but I have posted in that group. Okay, JEE, REP, some group is there. I have posted in that group. Repeat toppling. Okay, toppling next I will tell, then after this. Okay, shall I tell after this? Okay, first we will complete this. Now what is angular momentum about this point? It is angular momentum about center of mass plus angular momentum of center of mass with respect to this point. So what is angular momentum about center of mass is I omega, that is ICM into omega, plus angular momentum of center of mass with respect to this point, that is M into RCM bar cross VCM bar. Means you can extend velocity and drop a perpendicular, that is also in same direction, that is M into RCM bar and VCM bar are perpendicular anyhow. So M into R omega into R. VCM is R omega or V. So MVR, this is MVR and this is I omega. What is ICM? Gamma MR square if I write. Okay. Then what is angular momentum about O? Is MVR into 1 plus gamma L. This if you can remember directly we can use. Okay. So when a body is rolling on a fixed surface, then what is angular momentum of that body about any point which is passing through point of contact and parallel to velocity of center of mass is given by mvr into 1 plus gamma. Okay, mvr into 1 plus gamma. And kinetic energy I have told already earlier, it is half mv square into 1 plus gamma. This is kinetic energy when a body is rolling on fixed surface. Okay, and now here what forces are acting? Because what is velocity of lowest point now? Because of translation v naught towards right, and because of rotation 2 v naught towards left. So velocity of lowest point is v naught towards left. So kinetic friction acts towards right, and center of mass is C. Let us say point on ground here is A. A is a point on ground, and as it is moving, normal force acts here and mg will act here. And as it is moving, when it comes somewhere here, okay, here also friction acts in this direction, and normal force acts upwards, which is balanced by mg. Okay, n equal to mg. So about A, torque is 0 because frictional force passes through that point, and torque due to these two forces about any point is 0 because both of them are equal in magnitude and acting along same line of motion. Okay, then torque about this point is 0 on this body. Okay, that means angular momentum about this point is conserved. Okay, so once it starts rolling, what is velocity of center of mass? Let us say assume it is v. Then simply do angular momentum conservation about A. That's about A. So initially, what is angular momentum about A? Is angular momentum about center of mass I omega. Clockwise I'll draw it like this. Anti-clockwise I'll draw it like that. Or clockwise angular momentum we can represent with minus sign. Anti-clockwise with plus sign. Okay. And now what is angular momentum about center of mass? I omega. I omega clockwise. So minus. What is I? It is hollow cylinder. That is mr square into omega. Omega is 2v naught by r. Okay, I'll put minus. And angular momentum of center of mass with respect to point A means you have to drop a perpendicular from A onto center of mass, and rotation from r bar to v bar, that is also clockwise, and minus mv naught r. So LHS I have got negative. Finally, when it starts rolling also, angular momentum about this point should be negative only. But what is angular momentum? mvr into 1 plus gamma, because it has started rolling. Gamma is 1, so 2L. Okay, from here V value you will get when it starts rolling. How much you will get? LHS is 3V naught and this is 2V naught. So what is V? 3V naught by 2L. So when it starts rolling, what is velocity of center of mass? 3V naught by 2. Then what is angular velocity? Is V by R at that instant. Okay. Then after what time it starts rolling? Means because anyhow it is uniformly accelerated motion for center of mass, we can use V equal to U plus AT and all those things. Now what is initial velocity of center of mass? V naught. What is final velocity of center of mass? 3V naught by 2. And what is the only force acting on this cylinder? Is frictional force towards right, other than normal force and gravitational force. So what is the acceleration of center of mass? Mu g. Then you can use V equal to U plus AT. What is V? 3V naught by 2 equal to U is V naught plus mu gt. You can write like that. Okay. Any doubt? Then from here you can find time. Then what is work done by friction? Only force doing work is friction until it starts rolling. Once it starts rolling, friction do not act because there is no other force acting. Friction do not act. Then it goes with constant velocity. Velocity remains constant, omega remains constant, friction do not act. Okay. If there is another force, then friction may act to maintain rolling. If the applied force itself is maintained rolling, then friction do not act. Okay. And now what is work done by friction? Is change in kinetic energy. That is final kinetic energy minus initial kinetic. What is final kinetic energy when it starts rolling? Is half mv square into 1 plus gamma, where v is velocity of center of mass, which is given by 3v naught by 2. So half into m into 9v naught square by 4 into 1 plus gamma is 2 minus initial kinetic energy. Initially it is rotating and also translating, but not rolling. So you cannot use that formula. Separately you should write rotational kinetic energy and translational kinetic energy. What is translational kinetic energy? Half m v naught square plus rotational kinetic energy half I omega square. What is I? mr square into omega naught square, that is 2 v naught by r whole square, that is 4 v naught square by r square. Okay, that's what it is. Once you can see, if you have any doubt you can ask. Okay, for 2 minutes you see. Okay, no doubts I think. Now this is negative, I will get work done by friction. So similarly, one more question I will give. Will you try similar question? Okay. Now this is a solid sphere we will take. Solid sphere mass is m and radius is r, and velocity is given v naught, and angular velocity, let us say this is v, I will take, and omega is 3 v naught by r, and coefficient of friction is mu. Now in this case what happens? What is velocity of lowest point because of translation and because of rotation? If it is in opposite direction, then what happens is it acquires rolling after some time. But if velocity of lowest point because of translation and because of rotation is in same direction, also it will roll after some time, but it will reverse its direction. Either velocity will reverse its direction and angular velocity will reverse its direction. So either omega will become 0 in between or velocity will become 0 in between. If velocity becomes 0, it comes back, and when it starts rolling it will be moving towards left if velocity first becomes 0, and if omega first becomes 0, then it reverses its direction of rotation, and when it starts rotating it will be rotating in clockwise direction when it starts rolling. Okay, and it is also possible that both of them simultaneously become 0. In that case this body will stop. Okay, now first bit is I am asking, questions are same, after what time it starts rolling, after what time it starts rolling, then work done by friction in that time, then second, which one is becoming 0, means velocity or angular velocity. Okay, then finally last bit is find ratio v by r omega so that it stops. Okay, you can try by taking 2 or 3 minutes. Okay, then we'll continue later, next 2 or 3 minutes later. Now here, once again, if this point of contact on ground is here, let us, then what is initial angular momentum? Angular momentum about center of mass is I omega. What is I? 2 by 5 mr square into omega, that is 3 v naught by r, and this is anti-clockwise direction. So, I will take positive. And angular momentum of center of mass about A, that is m into v into r perpendicular, that is clockwise, that is m v naught r, okay, m v naught r clockwise. So, minus m v naught r. So, if I simplify this, what do you get? This is 6 by 5 and this is 1, okay. So, 1 by 5 I will get. So, this is m v naught r by 5 positive you have got, positive. Positive you have got means initial angular momentum about this point is anti-clockwise, means coming out. Finally, when it starts rolling also, it should be coming out, okay. But when it is rolling, due to both v and omega, angular momentum will be in same direction about point of contact. For example, if it is rolling and velocity is towards right, then omega should be like this, then clockwise angular momentum about this point. And if it is velocity is towards left and rolling, then omega should be like this, then about this point of contact is anti-clockwise angular momentum, okay. So, in this case, I have got initial angular momentum about this point anti-clockwise, means final angular momentum should also be anti-clockwise, means velocity should become 0. If velocity is towards right, when it is rolling, then omega should be like this, means angular momentum should be clockwise finally. And if velocity is towards left finally, then omega is like this, means its initial direction, angular velocity, means coming out, anti-clockwise rotation means coming out, okay. That means final angular momentum should be anti-clockwise, means velocity should be towards left finally, but initial velocity is towards right, and when it is rolling, its velocity should be towards left, means velocity should become 0 in between and reverse its direction, okay. So, when it starts rolling somewhere here, velocity is in this direction, let us see some v1, angular velocity omega, then v1 equal to r omega 1 at that instant. Then what is angular momentum? It is m v1 r into 1 plus gamma, mvr into 1 plus gamma, positive. What is gamma? 2 by 5, so 7 by 5. So, what is v1? Is v naught by 7L. So, when it starts rolling, what is velocity of center of mass? Will be v naught by 7 towards left, okay. And friction is acting in what direction? Towards right. Towards right, okay. Friction is acting towards left, not towards right, okay. Velocity is towards left, lowest point, so friction acts towards left, and friction throughout acts towards left, and initial velocity is towards right, final velocity is towards left, okay. And acceleration is how much? Center of mass is minus mu g. Then if I use v equal to u plus at, you will get time. What is v? Is minus v1, that is minus v naught by 7 equal to v naught minus mu g. So, 8 v naught by 7 by mu g, that is time. So, this is the time after which it starts rolling, okay. Then what is second bit? Velocity of center of mass and angular velocity when it starts rolling, we have found out anyhow. And work done by friction. Work done by friction is change in kinetic energy once again. So, what is work done by friction? Is final kinetic energy is half m v1 square into 1 plus gamma, that is 7 by 5 minus initial kinetic energy. What is initial kinetic energy? Translational kinetic energy plus rotational kinetic energy. What is translational kinetic energy? Half m v naught square plus rotational kinetic energy, half m, half I omega square. What is I? Half into 2 by 5 mr square into 9 v naught square by r square. initial angular velocity. Okay, this is work done by friction. Okay, and once it starts rolling, no friction acts because there is no other force acting. Okay, the next, what is relation between V and omega, and if it stops finally? Initially, if V is towards right and omega is like this, it has to stop finally. Okay, when it happens like that, if velocity becomes 0 and still omega is there, then it slips and after some time it starts rolling. Or if omega becomes 0 and velocity is there, and then also it starts rolling after some time. But if V and omega become simultaneously 0, where angular momentum of this body about this point finally becomes 0, then it stops permanently, it stays there. In that case, angular momentum initially about this point should also be 0. So, what is angular momentum initially about this point? It is angular momentum about center of mass, that is how much? 2 by 5 mr square into omega, that is anti-clockwise, so positive I will take, plus angular momentum of center of mass about this point, that will be clockwise, that is minus mvr equal to 0, that is okay. M also cancels. So, what is V? V equal to 2 by 5 r omega. Okay. So, what is V? V by r omega is 2 by 5. So, that is the ratio of V and r omega initially, and the directions are as shown. This solid sphere will stop after some time. Okay. Both stop simultaneously, velocity and angular velocity. So, next question we will see. Now, this is a uniform bar of length 6a and mass 8m lies on a smooth horizontal table. 2 point masses m and 2m, moving in same horizontal plane with speeds 2v and v respectively, strike the bar as shown in the figure and stick to the bar after collision. Denoting angular velocity about center of mass, total energy and velocity of center of mass by omega, E and V naught respectively, we have after collision. But questions did not ask, but does not matter. This is earlier IIT question only, and figure is incomplete here. There is another mass coming like this actually, m, moving with a velocity 2v. Okay, and because this is free to rotate and translate, this rod, and is on a smooth horizontal surface, free to rotate and translate, and these two collides and sticks, then linear momentum of the system is also conserved, and angular momentum about any point is conserved. But usually we will do angular momentum about center of mass, and center of mass of the rod is here. Okay, and this 2m is colliding at a distance a and sticking here. M is colliding at a distance 2a and sticking here. Okay, that means after sticking also, center of mass position of center of mass do not change. Center of mass divides the distance between the two particles in the inverse ratio of masses, and 2m is colliding at a and m is colliding at 2a. So, center of mass position do not change even if these two sticks. So, center of mass remains here only. So, immediately after collision, Q rotation is about the common center of mass, which is C only. So, assume it acquires an angular velocity omega like this immediately after collision, and velocity do not acquire, because if you see this figure, if I do linear momentum conservation, what is initial linear momentum of the system? This is 2mv in downward direction, this is m into 2v in upward direction, and rod has no velocity. So, what is initial linear momentum? 0, just before collision. Then after collision also linear momentum should be 0, means velocity of center of mass should be 0. So, center of mass do not move, this starts rotating about center of mass. So, it becomes pure rotatory motion immediately after collision. So, and this m collides and sticks here, and 2m collides and sticks here, and entire system rotates with omega. Okay. Now, if I do angular momentum conservation about this point, what is initial angular momentum? Is m into 2v into 2a, m into 2v into 2a, that is anti-clockwise, and for this 2m into v into a, this is also anti-clockwise. Okay. So what is initial angular momentum? Is 4 plus 2, 6 MVA. That is equal to final angular. Finally, it is pure rotatory motion. So what is angular momentum? I omega. What is I for the system? For the rod, what is mass? 8m and length 6a. So I will get 8m into 6a whole square, that is 36a square by 12, plus for this particle m into 2a whole square, that is 4ma square, and for this particle 2m into a square, that is 2ma square. So 6ma square, and this is 12 3s, okay, and 24 plus 6 30, you will get 30 ma square. That is moment of inertia of the system. Okay. So if this is equal to I into omega, if I write, what is omega? I will get by 30, you will get. So by 5 you will get. So V by A by 5. So this is angular velocity of rod immediately after collision. Okay, followed. See this, and if you have any doubt you can ask. Okay, 1 minute you take and see. You can type there and I will clarify. So this is angular velocity immediately after collision, and total energy, if they ask, half I omega square. Okay, what is total energy after collision? Half I omega square. What is I? 30 ma square into omega square is V square by 25 a square. That is energy after collision. What is energy before collision? Half 2mv square plus half m 2v whole square. So what is loss in energy during collision? Is initial kinetic energy minus final kinetic energy. Like that also you can do. Okay. And V naught respectively. V naught is velocity of center of mass after collision, I think that is the question. But V naught will be 0 immediately after collision. Okay. And immediately after collision, rod is only rotating, entire system. Okay. So today we will end it here. Okay. Next topic we will see next session. Thank you.